So today I'm reading Realm, Retrieval-Augmented Language Model Pretraining. It's from Kelvin Gu, Kenton Lee, Zoratung, Panapung, Pasupat, Mingwei Chang. So the abstract, just quickly, so far as I understand, what they do here is that they assist the model question answering scheme by providing additional, traditional search on the database, and results of that search they provide to the model actually. So it's a combination of a deep model with a sort of traditional text retrieval. Abstract. Language model pretraining has been shown to capture a surprising amount of world knowledge, crucial for NLP tasks such as question answering. However, this knowledge is stored implicitly in the parameters of the neural network, requiring ever larger networks to cover more facts. To capture knowledge in a more modular and interpretable way, we augment language model pretraining with latent knowledge retriever, which allows the model to retrieve and attend over documents from large corpus such as Wikipedia, used during pretraining, fine-tuning, and inference. For the first time, we show that to pretrain such a knowledge retriever in an unsupervised manner using masked language modeling and learning signal, and backpropagating through retrieval step that considers millions of documents. We demonstrate the effectiveness of Retrieval-Augmented Language Model Pretraining Realm by fine-tuning on challenging task of open domain question answering, OpenQA. We compare against required models for both explicit and implicit knowledge storage on 3 popular OpenQA benchmarks and find that we outperform all previous methods by a significant margin, 4 to 16% absolute accuracy, while also providing qualitative benefits such as interpretability and modularity. Okay, so what are main contributions, if I can find them quickly enough? Okay, let me see these main results. Table 1 shows accuracy of different approaches on OpenQA datasets. Realm outperforms previous approaches by significant margin. Table 1 also shows the number of parameters for each model. So let me see table 1. Okay, so here we go, table 1, test results. Okay, so we have for example, we have a BERT baseline. So that has results 26, 17, 21, while their model Realm has results 40, 40, 42. I think, wow, that's quite good. I think that's very good. And if we compare to ICT plus BERT, then the results are 43, 36, and 30. It's still, their Realm model is still doing much better. As reported in the concurrent work of Roberts et al. 2020, the generative OpenQA systems based on T5 are surprisingly powerful, with the largest T5 11 billion model outperforming previous best OpenQA system. Increasing the size of T5 yields consistent improvement, but outcomes at significant computational cost. From base to 11B, the model is 50 times larger and gains roughly 5 points in accuracy. In contrast, Realm outperforms the largest T5-11B model while being 30 times smaller. It is also important to note that T5 accesses additional reading comprehension data from Squad during its pretraining, 100,000 examples. Access to such data could also benefit Realm, but was not used in our experiment. Okay, I will find conclusion. Discussion and related work. Okay, language modeling with corpus as context. Language representation models have been incorporating context of increasingly large scope when making prediction. Examples of progression includes models that condition on surrounding words, Mikolov, sentences, Kiros, paragraphs, Redford, 2018. We can view Realm as a generalization of above work to the next level of scope, entire text corpus. to retrieve and edit with learned retriever. In order to better explain variance in the input text and enable controllable generation, Gu et al. 2018 proposed a language model with retrieve and edit framework. Hashimoto et al. 2018, the conditions on text with high lexical overlap. Realm has a similar approach, except the model learns itself which texts are most useful for reducing perplexity. By jointly learning the retriever, Realm has the capacity to depend on information beyond a lexical overlap. Scalable grounded neural memory. The document index can be viewed as a memory where the keys are the document embeddings. From this view, our work share motivations with work such as product key memory, Lampel 2019, which enables sublinear memory access in a memory network. Weston 2014, Grave 2015, and Subata 2015, allowing these scalable memory layers to be integrated into large language models. One main difference is that our memories are grounded. Each memory is associated with a document rather than unnamed value vectors. This level of interpretability is crucial for applications such as OpenQ&A, where users would require provenance from predicted answers to be trustworthy. Okay, so they have this feature of provenance, right? They have explainability. So if you want to know why model answered like this, you can see the source text, right? That's source text. That's excellent. Unsupervised corpus alignment in sequence-to-sequence models with attention. Bahadao 2014, text is generated with latent selection of relevant code tokens. This result is set of model-centric unsupervised alignment between target and source tokens. Analogously, Realm also generates text with latent selection of relevant documents. And byproduct of our method is that we offer a set of model-centric unsupervised alignment between the text and in the pretraining corpus X and knowledge corpus. Okay, future work. Okay, let me backtrack to the introduction. Okay, introduction. So recent advances, Roberta, BERT, predict missing word. Word knowledge is stored implicitly in parameters. To capture knowledge in more interpretable and modular way, we propose a novel framework, Retrieval-Augmented Language Model, ReALM, pretraining, which augments language model pretraining algorithms with learned textual knowledge retriever. In contrast to models that store knowledge in their parameters, this approach explicitly exposes the role of the world knowledge by asking the model to decide what knowledge to retrieve and use during inference. Before making each prediction, the language model uses the retriever to retrieve documents from large corpus, such as Wikipedia, and then attends over those documents to help inform its prediction. Learning this model end-to-end requires backpropagating through retrieval step that configures an entire corpus of text knowledge, as shown in figure 1. Okay, so let's have a look at the figure 1. So here we go, unlabeled text from pretraining context, and then they have a mask in some sentence over here. Textual knowledge corpus. So they have this input of unlabeled text with a mask. They retrieve from the textual knowledge corpus with neural knowledge retriever. Okay, so the retriever is also neural. They retrieve the document. For example, here the document is pyramidon on top, allows for less material higher up in the pyramid, while the sentence is missing a mask, which seems to be possible to replace with pyramidon. They query the document, so they specify class, and then they have the masked sentence, then they have separated token, after that there is this context knowledge from the corpus. And then they use knowledge augmented encoder, which produces answer that the mask is supposed to contain pyramidon. And so here they say the realm augments a language model pretraining with neural knowledge retriever that retrieves knowledge from a textual knowledge corpus. Is that, for example, our Wikipedia. Signal from the language model objective propagates all the way through the retriever, which must consider millions of documents in Z, a significant computational challenge that we address. Okay, so let's go back. Okay, let's go back. Retrieval-Augmented Model with the textual knowledge retriever. Context to the models. Figure 1. The key intuition of Realm is to train the retriever using a performance-based signal from unsupervised text. A retrieval that improves the language model's perplexity is helpful and should be rewarded, while informative retriever should be penalized. For example, in Figure 1, if the model needs to fill in the blank, the something at the top of the pyramid, the retriever should be rewarded for selecting the element containing the pyramidion on top for less material higher up the pyramid. We achieve this behavior by modeling retrieve then predict approach as a latent variable language model and optimizing the marginal likelihood. Incorporating large-scale neural retrieval model during pretraining constitutes a significant computational challenge, since the retriever must consider millions of candidate documents for each pretraining step, and we must backpropagate for its decisions. To address this, we structure the retriever such that the computation performed for each document can be cached and asynchronously updated, and selection of the best documents can be formulated as a maximum inner product search, MIPS. Numerous previous works have demonstrated the benefit of adding discrete retriever steps on neural networks. Miller 16, Chen 17, but did not apply the framework to language model pretraining and employed non-learned retrievers to handle large-scale document collections. In language modeling literature, K-nearest neighbored language model, Handeval 19, KNN-LM, retrieves similar LM example to improve memorization. However, KNN-LM was not fine-tuned for downstream tasks, perhaps because it is unclear how to adapt the retrieval mechanism. The KNN can only use examples labeled for the target tasks. During the fine-tuning, this precludes LM examples which contain desired word knowledge. In contrast, realm retriever is designed to transfer other tasks, and retrieval is just a text, not a labeled example. We evaluate our approach by fine-tuning the model pre-trained with realm on tasks of open domain question answering, one of the most knowledge-intensive tasks in natural language processing. We evaluate on popular OpenQA benchmarks, natural question, open web question, curated track, and compared it to the state-of-the-art QA models, including both relatively extremely large knowledge and previous approaches, significantly outperforming all previous systems by 4 to 16% in absolute accuracy. We also demonstrate qualitative benefits of Realm, including interpretability and modularity. Okay, actually, let me have a look at number of those parameters in table 1. So yeah, here in the table 1, right, I mentioned that they do much better than, for example, bird, right? They do much better than bird baseline. And but the bird baseline has 223 million parameters. Their real models has more than that. They have 330 million. And other bird 110. Actually, they do have more parameters, right? But then, if you look at the T5 transformer seek-to-seek multitask, that one has many more. There's 11,000 million, like 11 billion parameters, but does actually much worse. So they seem to be right. They need less parameters, right? So where we are. Language model pretraining, open domain question answering approach. Retrieval language model pretraining. The goal of the language model pretraining is to learn user representations of the language, usually from unlabeled corpora. The resulting pretrained model can be further trained, fine-tuned for the downstream tasks of primary interest. In our case, on the main QA, often leading to better generalization than training from scratch. We focus on masked language model variant of pretraining popularized by BERT. In its basic form, the MLM is trained to predict missing tokens in the input text passage. Given an unlabeled pretraining corpus, for example Wikipedia text, a training example can be generated by randomly masking the tokens in a sampled piece of text. The model uses its representation of masked input to predict the token that should go in each mask. A good LLM must learn to encode simultaneous semantic. Okay, I think that's obvious. Approach. So they have this retrieval and predicts. RAM's generative process. For both pretraining and fine-tuning, RAM takes some of the inputs and learns distribution P condition on X of Y over possible outputs of Y. Pre-training, the task is masked language modeling. X is sentenced from pre-training corpus X with same tokens masked out. Y fine-tuning realm decomposes P condition Y conditioned on X probability into two steps: retrieve and then predict. Given an input, we first retrieve possible helpful documents Z from knowledge corpus. We model this as a sample from distribution period, then condition on both retrieved and original input. Alright. Model architecture. Knowledge retriever. The retriever is designed as dense in a product model. Okay, so here we see the softmax and off function where we have embeddings of the documents and they're in the product. We're embedding functions that map X and Z respectively to d-dimensional vectors. The relevant score between X and Z is defined as any product of vector embeddings. The retrieval distribution is also mapped over the relevant scores. We implement the embedding functions using BERT-style transformers. Following the standard practice, we join span the text by applying word-piece tokenization, separating them with separation tokens, prefixing class tokens, and appending final subtoken. Okay, knowledge augmented encoder. Given X and Z document, we join X and Z into single sequence. And feed it into the transformer. Yeah, I think that was explained on the beginning, right? This input, they sort of concatenate the context and the masked sentence, and then they do the search. Okay, so how they do the training actually? We still need an efficient way to find top K documents. Note that the ordering documents under P conditioned on X of Z is same under the relevant score embeddings, which is in a product that we employ maximum inner product search algorithms to find approximate top K documents using the running time and storage space that scale sublinearly with number of documents. Raman Gray 2005, Srivastava 2014, Shen 2015. We employ MIPS. We must precompute embedding for the every Z and construct an efficient search index over these embeddings. However, this data structure will no longer be consistent with Z condition on X if the parameters theta of the embedding document are later updated. Hence, the search index goes stale after every gradient update of theta. Our solution is to refresh the index asynchronously, re-embedding and re-indexing all documents every several hundred training steps. The MIPS index is slightly stale between the refreshes, but note that it is only used to select the top K documents. We precompute P condition on X and its gradient using the fresh theta for each top K documents after retrieving them. In section 4.5, we empirically demonstrate that this procedure results in stable optimization provided that the refreshes happen at sufficiently frequent rate. Okay, implementing asynchronously MIPS refreshes. We asynchronously refresh the MIPS index by running two jobs in parallel, primarily training jobs index builder. So they have index builder trade-off. So we have a figure 3 realm for training with asynchronous and MIPS refreshes. While asynchronous refreshes can be used on both pretraining and fine-tuning, in our experience, we only use it for pretraining. For fine-tuning, we build the MX index once for simplicity and do not update embedded documents. Note that we still fine-tune embed input, so the retriever function is still updated from the query side. Okay, what does retriever learn? Since the document retriever RAM is latent, it is not obvious how the training objective encourages meaningful retrieval. Here we show how it rewards retrievers that improve ratio accuracy. For a given query X and the document Z, recall that f of X and Z is a relevant score that the knowledge retriever assigns to the document Z. We can see how a single step of gradient descent during pretraining alters the score by analyzing the document gradient with respect to parameters of knowledge retriever data. So they have this gradient of logarithm of p condition, p of y condition on x. Then they have sum over all documents of r multiplied of z, which multiplies the gradient of that function. I think that's the multiplication function, where the area of z is this function of the depending on the probability conditional probability distribution. For each document, the gradient encourages the retriever to change the score. The term P is the probability of preceding the correct output Y when predicting the output Y when using the command Z. The term is expected value, then randomly sampling the document has the command Z retrieves the positive update whenever it performs better than expected. Okay, so the command Z receives positive update whenever it performs better than expected. Okay, let me go forward. I'm running out of time. Okay, future work. The work presented here is the minimal instantiation of the family of realm-like approaches, where the presentation is pre-trained to perform reasoning over a large corpus of knowledge on the fly during inference. We are particularly optimistic about generalization of this work to structured knowledge, which would result in a generalization of Peter's 2019, where we would also learn the decisions of which entities are informative. The multilingual setting, a retrieval knowledge in a high resource language to better represent text in a low resource language. And 3, the multimodal setting, for example, retrieving images or videos that can provide knowledge rarely observed in text. Okay, thank you very much. I hope you liked the video. Never ever subscribe or like these videos. And yeah, I'm surprised you made it till the end. Thank you very much. See you next time. Bye bye.